Welcome to the demonstration corner. Today we'll be talking about the transient hot wire for the MP-1. Transient hot wire being an absolute method for measuring the thermal conductivity of fluids and paste and phase change materials. Tradition here at the demo corner is we do a little circle to show the methods that are here that we can use to demonstrate how that thermal conductivity is not a simple measurement. It really is a measurement that requires sometimes unique methods, and other times generalized methods can be used. So starting on this side, this is a heat flow meter following ASTM C518 and other international standards for measuring insulation and construction materials. It works off the principle for highly heterogeneous materials. You're measuring the thermal resistance and thermal conductivity of large sample size. This is a guarded heat flow meter, so it follows similar steady state principles, but it uses a guard to limit the amount of lateral heat loss so that you can measure complex heterogeneous materials or layers of materials, and it measures the thermal resistance and thermal conductivity across the one-dimensional plane. Again, the guard is what enables you to measure across that one-dimensional plane. This follows ASTM E1530, thermal conductivity range of 0.1 to 100 watts per meter Kelvin and up to 300 Celsius. The heat flow meter, which was the method I pointed to earlier, that is on the range of 0.001 watts per meter Kelvin up to plastics. We have our MP-1, which we'll be talking about in a minute, so let's just continue on. This is our transient plane source meter. Following ISO 22007-2. This is primary designed for measuring solids, pastes, and powders. Conductivity range, overall conductivity range, 0.01 to 500 watts per meter Kelvin. Temperature is based off of what accessory attached to it. And another principal primary method is our transient hot wire, our THW L1. This allows measurement of thermal conductivity, thermal diffusivity, and specific heat according to ASTM D7896. The overall temperature range is cryogenic up to 300 Celsius. Of course, we have different ranges in that temperature based off of the model. The key parameter of this method is the way it measures conductivity with a wire. In addition, you can back pressure the cell to allow you to test past boiling points. Controlling convection is key. And then going further down the demonstration corner, which is videos we've done at other times, is our small heat flow meter, our HFM25. It follows the same standard as our large heat flow meter, C518, but it is designed for measuring small format insulation. And then our MP2, our measurement platform 2, which has primary sensors, transient plane source, transient hot wire, transient line source, all smartly packaged within a portable economic device. Really is the baby brother to the measurement platform MP-1. So coming back to the MP-1, what we did is we brought the two instruments that I just talked about, the TPS-2 and the THW L1, into one instrument to pack a big punch. So this instrument has a lot of capabilities. The MP-1 itself has the ability to attach a sensor in the front as well as other devices. There's one port in the front and 3 ports in the back, and you can even expand that to another 8 ports. The point being that you can attach multiple devices to the same controller. So every MP-1 controller comes with that capability. There's a smart screen for showing you which port is being measured at different points, and the software we've built to take advantage of those ports has the ability to schedule multiple sensors and or temperatures at the same time. So you can walk away and, so we've had configurations where customers want multiple transient hot wire for large volume testing or multiple transient plane source. As you can see, it is all modular. So if you want to just do room temperature, you can get the MP-1 with just the controller for room temperature testing. Same port, so you can do multiple room temperature testing. But you can also join with it our temperature platforms. This is a transient plane source temperature platform. This is a transient hot wire temperature platform. These both, based off of the temperature range you require, have ranges of minus 160, minus 45, 0 to 200 and 300 Celsius. So the overall full temperature range of these are 300 Celsius all the way down to cryogenic if you need it configured that way. What we have here is our base temperature platforms. The base temperature platform for the THW is 10 to 200 Celsius. Key being it doesn't require any external cooling. It's thermoelectric cooled. This is a unique capability that ThermTest offers within our MP-1 is the control of temperature. Excuse me. We have very precise control of temperature because of the proprietary method we've designed. It's all housed. So if you wanted to, you could put 3 or 4 of these next to the controller and you would have a lot of throughput for any of those methods. The other method we've recently added to the MP-1 is the transient line source. So really there's quite a few capabilities within this technique. And that was always the intent, the MP being something that is modular that we can build onto. So what we're here to talk about is really the transient hot wire method for measuring liquids, phase change materials, paste. You can also do powders, depending on the nature of the powder. Small particle is really best suited for THW. Larger particle are better suited for the transient plane source method. We'll cover that in another video. So I'm going to pull this a little closer to the camera, talk a little bit about the sensor that we have. So I'm going to try to get this focused. We're going to do our best. So there is a platinum wire that's suspended between 2 contact points. You can see there's a screw that connects the wire on the bottom, and then there's another screw that connects the wire on the top. Hopefully you can see that. It is a little difficult. It's a very thin platinum wire. The principle there is that we pass a current through that wire and we generate a small amount of heat. This is this sensor would be inserted into a container with fluid, a cell for fluid with fluid in it, and we'll show you this setup, but that would be your containment. It holds about 20 milliliters. And once a measurement is done, all the measurements for fluids are done at 1 second. Power is selected based off the thermal conductivity of your fluid. So the software, the intelligence software actually probes this sample with a small amount of current to determine its thermal conductivity range and optimizes the power based off of a 1 second test time to achieve the ideal temperature rise. So there's no iteration, there's no guessing of what the power is. It's all fully automated within the software. So that sensor, it is uniquely designed to control convection. So this sensor with the ability to back pressure allows you to test a wide range of viscosity. Convection is the enemy when you're trying to measure thermal conductivity with methods that are designed for solids. This is a primary method that's used for design for measurement of thermal conductivity, diffusivity, and specific heat of fluids. This does follow the standard ASTM D7896 for those 3 properties. So if you're only testing within a temperature range that you don't have convection due to temperature rise and or the temperature that you're testing at, the ambient temperature, you can probably don't need to pressure it, but as you go near boiling points or your evaporation of your fluid, you might need to back pressure it to allow you to test and keep the fluid in the liquid phase. The 2 back pressure ranges are 20 bar and 35 bar. Those are the 2 pressure ranges you can use to really extend the use of this sensor. So I'm going to put this down, and there's something to talk about when it comes to fluids, and that is the other methods of measuring fluids that are used in the market. We have our transient plane source. There's multiple makers of transient plane source. The idea being with transient plane source that you limit the amount of volume you measure by using a very small diameter sensor. So very typical is a 4 millimeter sensor. We also have cells that allow you to really minimize the amount of volume, because by minimizing the amount of volume, you reduce the effects of potential convection within the fluid. Again, with the idea of testing lower viscosity fluids. But even then, as you get lower in viscosity or even higher in temperature, closer to the boiling points, often you have to input the volumetric specific heat of the fluid to correct for the complexity of the sample. So although you could optimize this primary methods for solids to test fluids, you really have to be careful, and it's a complex measurement. The other method is the calibrated modified transient plane source. This does use liquids to offset the heat sinks that are within its design. This is around a 13 millimeter diameter. it would suffer from the same effects of convection. Convection is effects of buoyancy. You can't correct for that. You can only limit it. Often for lower viscosity fluids, you have to input the volumetric specific heat of your fluids to test those as well. The other method that is, because it's a lower price, is the transient line source. This is a 60 millimeter transient line source. This, although it is small compared to the transient line sources that Thermtest offer, we offer a 100 millimeter probe, which is used 100 millimeter and 150 millimeter. Those are exclusively used for non-liquids or very high viscosity fluids, true. But the test times are into the minutes of those longer probes. So this transient line source needle measures a fluid for 1 minute. Within that 1 minute, you're creating a large delta T that will give you effects of convection. There's no way to correct for that. So there's a lot of publications that show use of this needle for measuring fluids. And you'll see that as you get into water and lower viscosity in the water, that the results are often skewed by convection. And that's a really important point. So if you're looking for accurate values of thermal conductivity of fluids, you have to consider these things. So getting back to our transient hot wire sensor. So we're going to bring the camera in a little closer so we can show setup. So when you buy a MP-1 with THW method, you get a cell. This cell has some convenience elements. So it has a nut pattern on the bottom. And there's, as you can see in this holder for the cell for loading it, there's a nut pattern. That's so when you disassemble the cell, you can, that can be pushed in there and affixed so that when you turn it off, you have something to hold on to. So it gives you two mechanical movements so that you can release the cell. The reason why there's a little bit of tension is because there's an O-ring. That O-ring is what we use to seal the cell so that we can apply back pressure if needed. And those O-rings come in different types to go to cryogenic and up to 200 or 300 C depending on your test cell. So when we load our cell, which holds around 20 milliliters of fluid, we're going to load this one. We typically fill it to the ridge there, you can see. So I'm just putting in water. It'll be hard for me to show this because it'll just spill out, but I'll try. So essentially, you can see the fluid in there. That's about 20 milliliters. And then we would insert our cell, rather our sensor, and turn it. So if I was taking this apart, I would just do this all in reverse. So you would turn it. Of course, if I was doing this on the bench, it'd be a little easier. And you would turn it until it's sealed. And now you have in this case, a silicone gasket sealing it. It's completely sealed. This is your back pressure line. Right now it's just open, so it's ambient. We're not applying any back pressure, but if you did have evaporation, you want to contain the pressure or add extra pressure, this is the line you would use. And now that we've loaded that cell with water, we can take the adapter off. And before we go over and put this into the temperature platform and connect it to the MP-1, I wanted to show you something. So these are the additional cells that you can get with it. You'll see from the demonstration that we mentioned phase change materials. So in this cell, it's completely open. And what you do is you would insert your sensor upside down. And if you were measuring phase change materials, you would pour the liquid in, rather the sample in a heated side, so it's in the liquid phase. And this is the plunger bottom that we use. This plunger bottom, as you can see, allows for about 15% change in volume. The key there is that as the sample changes in volume, it maintains contact with the wire. That's really important. So you would fill this to a point and then screw this on, and that would allow you to apply a little bit of mechanical pressure to apply so that the phase change material stays in contact with the wire. That's really important. The other versions of that, same cell, just different approach. If you want to measure powders or materials that you want to set the volume, this is an adjustable variable density fits in, and you can, there's an Allen key, hex key, and then you would just turn this up or down depending on how much pressure you want to apply, and that goes up and down about 15% as well. So those are the different phase change cells, and with phase change you can have very good results, both increase in temperature, or when you're decreasing temperature, you can see the effects of that. I'll show you a link on the website where some of the data we have, but that's our phase change cell and powder cell components. The other cell that you can get for it is an observation cell. So this would be with a glass container, same connecting portion on the top. This is good for if you want to see if you have phase separation or settling of micron or nano size particles. You can sort of make some measurements and see the change, both thermal conductivity, thermophysical properties, as well as inside the cell. So that's what we call our observation cell. So at this point, I'm going to bring this over to the MP-1 and put it inside the temperature platform. So we'll put it inside the temperature platform. This is what we use when we want to make measurements at temperature. Of course, if you just want to make measurements at room temperature, when you have an MP-1 with the transient hot wire method, you get a very simple to use transient hot wire sensor for just making room temperature measurements. So of course, not all measurements need to be made at temperature, but most users of the transient hot wire are looking for measurements with temperature. So we would make a connection. There's a dot here. We'd line that dot up with the front of the temperature platform, and now that connection is made. So I'm going to go to the software now and walk you through the steps of making a measurement. Right now you see the temperature of the temperature platform is set at 25. That's just the sitting temperature, if you will. Now we'll go to the software and switch cameras so you can see that. So you should be seeing our screen. This is our data acquisition software for the MP-1. We've divided the software up into two applications. So the data acquisition is what controls the controller, the switches, the parameters, and as well as the automation of those parameters. So it allows us to have a lot of power in controlling a single sensor or multiple sensors to really get the best experience and convenience out of the software. The second application is the analysis or raw data or results analysis software. We call it the Transient Analysis application for the MP-1. It allows us to pull in the data from the MP-1 and analyze it in a very convenient, powerful way. So instead of trying to compress this all into one application, we've separated it in two applications to give you the best experience possible. So here's our, right now, this is our home. This shows everything that's connected to the MP-1. It auto-detects everything, so you have MP-1, two temperature platforms, and a room temperature sample holder. That's just based off other work we were doing before we started this demonstration. This is our make an experiment. You browse to the location you want to save your data. Here are the methods that this software has enabled. Being a demonstration, of course, we have all of them. One-dimensional plane source, three-dimensional plane source, direct specific heat, transient hot wire for liquids, and transient line source. And we're going to use transient hot wire for liquids and powders. There is no modules because this is the complete capability of this instrument. So next, it self-detects what's connected to it. Here we could do a room temperature or the different temperature platforms. Of course, we're going to select the THW temperature platform, and that's what is changed. If you selected a different one, you would see a different temperature platform. And here it complains, it says not compatible with the THW. Of course, we have set the sample up in the, not compatible with TPS. We've set the measurements up in the transient hot wire. And that's the serial number of the device. So if we click next, here we have our parameters. So I can name my sample. If I want to, I could put in the boiling point. These are all just notes for you for later consideration. Here it shows all of the sensor ports. Of course, we have our THW sensor plugged into the third port, and we can do a quick ohm check on that sensor to make sure we haven't broken the wire or there's no physical damage to the sensor before we take time to make measurements. So it's doing a quick resistance check. It's good. So now I'm going to go to next, and here is where I put in the temperature steps that I want. So I can, the easiest way, if you want to run multiple temperatures, is to use add a range of items. So by clicking range of items, let's say I want to do 25 to 100 degrees C in increments, 100 degrees C in increments of 25. And I add to schedule. So in this case, I've set it to run 3 measurements with a 5-minute delay, add schedule. And it automatically builds the schedule for going to 25, 50, and 75, and 100, and optimizing the power. That's what this means. Is instead of inputting manual, it optimizes the power. Here is sample stabilization. So this is the criteria for the temperature platform that is default. It says go to a temperature, stabilize at isothermal conditions, and then proceed with measurements. And as soon as I click start, it goes to our in progress measurements and starts to go to 25 degrees. Now, of course, the temperature platform is already at 25 degrees. It will go through the 2 steps of stabilization, which is there should be a certain stability at the furnace level, and then there's a thermocouple, or rather a PT sensor inside the THW sensor. It will monitor that for a length of time. So it's looking for 2 levels of temperature stability, one at the controller level for the temperature platform, and second at the sensor level. So it's recording the temperature directly from the sensor for reporting thermal conductivity. So and then it'll proceed on to step 3 for 50, step 2 for 50 degrees, 75 degrees, and 100 degrees. So right now, it'll just proceed with those temperatures and make those measurements. We ran a measurement before the live demonstration using the transient hot wire. I'll expand this and show this, but in addition, you can see that I had been running one-dimensional measurements, and so you can see you can mix methods and have it all scheduled within the same software. So here is transient hot wire, complete measurements on 10, 20, 30, 40, 50, 60, and up. You can see it gives you early results of thermal conductivity with temperature. This first one being around 10 degrees. It gives you early results on thermal conductivity. If I go to 20 degrees, it shows you my measurement of water was 0.6016, and diffusivity and volumetric specific heat. So all of that's optimized. And we can look at any one transient to look for the residual pattern. We want a nice random residual there. But that is better done inside the thermal analysis software. So here's my thermal analysis software. I've imported all of that data. I've just, it auto-calculates it. You can show one experiment, and you can show the results for one experiment, or you can show all of them, which is up to 54 degrees. And here you can see our raw data, temperature rise versus time, our residuals, the fitting, and our bulk results. You can see we've averaged of three measurements at each temperature, and here's our average of 3 measurements at 20 degrees. And there's, you can see our stats. So at 20 degrees, our average was 0.5999. I think that was 20 years, yeah. So that is really, and if you want to look at individual residuals, you can. If you want to combine other methods within the software, you can open them up and analyze different sets of data all within the software at the same time. You can export all of this to Excel, and it generates all the data. And that really is the entirety of the thermal analysis. Its sole function is to really automate as much as possible the analysis of data and make it convenient to open and deal with lots of data. Obviously, with a 4-channel switch and the ability to use multiple methods, there's a lot of data you can generate. We wanted to create a platform or an application that was convenient to that volume of potential data. So that's transient hot wire for measuring thermal conductivity, thermal diffusivity, and volumetric specific heat on fluids, covering a wide range of viscosity on the measurement platform, or the MP-1. And I think that concludes our demonstration. I will stay online to answer any questions on YouTube in the comment box if you have any. Otherwise, I think we're done. Thank you for your attention. Appreciate the time.